I'm in charge of number 1 again. So this one, we're going to be dealing with chi-squared, and the question is, suppose that you're interested in studying the inheritance of 2 traits in garden peas. So we're going to be looking at color and our pod shape. It's the cotyledon color. I'm not sure if I'm saying that right, but we'll go with it. Cotyledon color could be either yellow or green, green being dominant, yellow being recessive. And then our pod shapes, constricted being dominant and inflated being recessive. And that'll kind of come out to be our null hypothesis at the beginning of our crosses. So you set up a cross between a true breeding plant with green cotyledons and inflated pods with a true breeding plant with yellow cotyledons and constricted pods. All of the F1 plants have green cotyledons and constricted pods. You then self-fertilize F1 plants and obtain these results. So these are going to be considered our observed results from our testing. But for A, we're going to have our null hypothesis, and B, we're going to use these in order to figure out our chi-square equation over here. So first, we got to figure out our expected values, which you just total up the number of observed values that we have and multiply that by the expected ratio. So remember Mendel's law with the law of segregation and assortment. His ratio came out to be the 9:3:1 ratio, and that's where we get our fractions from over here. And since we think that dominant is our green constricted, that's the one that'll start with 9, and then you just go down from there. All right. So once you get your expected values, which you get here from multiplying those across, we can actually find out our chi-square by plugging all of these values in. So chi-squared is the sum, as you can see, these are all adding together, of our observed minus our expected value squared over our expected. So we've just plugged these in right here, as you can see, and our value came out to be 43.56. And then we got to figure out our degrees of freedom. We have our 4 phenotypes, and degrees of freedom, I'll just write the equation real quick, equals n minus 1, so n being our categories, minus 1, and that's how you get 3. So once you get that, you can go in and look at this chart. You can kind of see here, this wonderful chart that was on the PowerPoint. So you got your degrees of freedom over here. So we got 3. You just come down to 3 and move across until you find.
Yeah, the light's just kind of shining.
Oh, I'm sorry. That's okay. You can look this up, right? Okay. And then you just look to see if your value under 3, you just keep coming and coming. And if it's not there, if it's higher, like the last one on here is 11, and it's in the dark shading, we know that you're going to be rejecting your null hypothesis, because this is definitely much higher than 11. So since we reject our null hypothesis, on D we have to go back and propose a new one. For what we did, we just took our old hypothesis and swapped these two. So our new hypothesis would be our yellow being recessive, or yellow being dominant, green being recessive, constricted being recessive, and inflated being dominant. And then you could just test it again. Yep, that's one.
You're covering the mic.
Ooh, squeaky.
All right, so for number 2, we're talking about mice and shakers. So it says, in mice, shaker head tremors is thought to be controlled by a gene on the X chromosome, and the autosomal influence of coat pigmentation, which I've shown right here, is we have big B for black, and etc. So our first question says, based on what we have learned in class, what inheritance pattern best describes the coat pigmentation in mice? So looking at this, seeing that black and white are both shown in the heterozygous and they don't mix, we know that it's going to be codominance. For part B, it says, determine the genotypes and the phenotypes of the F1 offspring. Well, we know that we have a true breeding black female, which is what we have. Where did I put it? Yeah. But here we have the true breeding black and the true breeding no tremors for the female. And then we breed her to a shaker white male. So we have this genotype right here, little b, with the male genes. So our genotypes and phenotypes we have represented right here. All of our offspring, male and female, are going to be black with white spots. And right here we're going to get 2/4 of our females that are normal, and 2/4 of the offspring are going to be male and normal. So we're not going to have any shaker children. For part C, we're performing the chi-square analysis to examine the null hypothesis that the shaker gene is X-linked and the copigmentation is found on an autosome. So we have our chi-square equation right here. Observed minus expected squared over expected. Just find the sum of that. So right here we have our F1 offspring, and we have the genotypes and the phenotypes shown. So we get 1/4 of our offspring are going to be black, 2/4 are going to be black with white spots, 1/4 are going to be white, and then 2/4 of our offspring are going to be shakers, and 2/4 of them are going to be normal. And what we have right here is our observed and expected values. So the observed we received just in the question, and then our expected values is what we get from the Punnett squares. And if you look right here, we have 2/16 normal black, and we're going to multiply that by 26 because that's our total from the observed values. We get all our values from that. And then we go up here. This is a big mess. You don't really need to look at it. It's just showing the work. But here's our chi-squared work. Our eventual chi-squared value was 6.92. Our degrees of freedom is 5, and that's because we have 6 different categories. Degrees of freedom is n-1, so we get 5. Our p-value is 0.05 because that's the most common statistical p-value. So for part D, we just interpret our chi-square value, and we decided that we're going to fail to reject the null hypothesis because the number was in the light gray area rather than dark gray. And that's it for my work.
Alright, I'm just going to apologize to everyone in advance because you get to deal with me with 3, 4, and 5. Unfortunately, 4 and 5 are the easiest, so it's kind of hard to say, I'll do 4 and 5. Okay, so for number 3, it says, suppose you're studying the inheritance of the grin and disappearance traits in a rare breed of Cheshire Cat. The grin trait is controlled by a dominant allele, which will be our big G, and a recessive allele for small grins, which is our little g. An independent assorting gene controls the disappearance trait and can exist either as a dominant disappearance or a recessive non-disappearance allele. So first off, we're going to square a heterozygous for both genes on both the male and the female side. This will be our big Punnett 4x4 Punnett square coming out. These will be our phenotypes, the ratios that they have. Sorry, these will be our genotypes, the ratios, and then these will be our phenotypes. We've got large grin disappearing, large grin disappearing, large grin non-disappearing, large grin disappearing, large grin non-disappearing, small grin disappearing, and small grin not disappearing. So using all of this information, we come over here to letter A. Letter A asks, what is the probability that the first 5 offspring has small grins and can disappear? So for our small grins that can disappear, we had 3/16 of the ratio. Did I do that wrong? So it's actually going to be 5. So my number might be a little off. No, it's not off. I just did it wrong. I just wrote it down wrong. Okay, so it's 5 here. Don't know why I put 4 and then 5 there. So as all comes out, all the math comes out. This number times by 100 to get our percentage, we're 0.023% probability that the first 5 offspring will have small grins and can disappear. For B, we had to do the binomial equation. I can't remember for some reason the middle words slip in my mind. But for that equation, we get our I exclamation point all over 5 exclamation point times by our 3 exclamation point. Now all of this by our phenotypic ratio for whatever. All of our math here together. You know how to plug it into the equation, figure it all out. All of this comes out to this, which equals our 0.08% percent chance that the out of the 8 offspring, 5 will have large grins and can disappear, and 3 will have small grins and cannot disappear. For letter C, it says, what is the probability that an individual offspring can have a small grin and can disappear, or have a small grin and cannot disappear? For this, we have to do the sum rule. So we have our 3/16 that can have a small grin and disappear, and our 1/16 that can have a small grin and cannot disappear. Added those together comes out to 4/16, which rounds down to 1/4, which is equals to our 25% chance that the offspring can have either one of those phenotypes. For letter D, it says, what is the probability that the first 4 offspring have large grins and can disappear, and the next 4 offspring have small grins and cannot disappear? So our phenotypic ratio for that to the 4th for the first option, then to get both of them together, we had to times it by that second phenotype ratio. Comes out to this big old long number, times by 100 is 0.000153% chance that you'll have the first 4 with that first phenotype and the second 4 with the second phenotype. All right, for the number 4, we're gonna make it fun. Pick on, right? See if that works. Okay, so for number 4A, we're given this pedigree chart, and we determined that it was autosomal dominant because both males and females were affected, and an affected offspring always has an affected parent. And these options. Okay. Forget not everything's touchscreen in my world. For letter B, we have Y-linked due to the fact that only males were affected, and every single male that was affected had a father that was affected. So it was handed down from father to son only. And letter C. So letter C, we picked X-linked recessive because it skips a generation. Where'd it go? Oh yeah, sorry. Skips this first generation here, then we have an affected one in every generation after that, except for here, which is another skip generation. So it's not autosomal because the males and the females, okay, sorry. It's not autosomal because just the males are affected, right? Is that what we decided?
Females are affected.
Yeah,
Autosomal.
sorry. It's not autosomal because males and females are affected, not just males. Which recessive dominant would be. Whatever. Anyway, X-linked recessive. That's what we got. Don't listen to my blabbering. And for letter D, wait,
This one's the X-linked recessive.
Yeah.
where did I get? Oh, my bad.
Pretty
Go
sure
back,
3's
sorry.
autosomal.
Backtrack, everybody. Okay, so this one is autosomal recessive. I skipped a number. My apologies. So this one is autosomal recessive because the males and females are affected, and that 2 unaffected parents can produce unaffected offspring. Okay, sorry. Moving on to D. This is the one where I had to do it. Okay, so D is an X-linked recessive because it skips the first generation here, and only the males are affected. And because it can't be a Y-link because dad's not affected here to hand it down. Alright, last but not least, we have letter E. So letter E has got autosomal recessive because all of the offspring that have 2 affected all the offspring of 2 affected individuals are affected. So because these two are affected, these two are also affected, which gives us our autosomal recessive. Okay, so for our fill in the blanks, we're just going to turn this off. Okay, so we're just gonna give those answers reading to you. So for A, we have the sum probability rule is used for mutually exclusive events, while the chi-squared test, chi-square test compares the observed outcome of a genetic cross to what was expected. For B, we have more males are affected than females when a trait follows an X-linked recessive inheritance, while an affected male produces 100% effective daughters when a trait follows an X-linked dominant inheritance. For letter C, we have when calculating probability, the word or indicates that one would use the sum rule, like we did over here. In letter D, it says in probability, the term independent events is used to describe events that have no influence on each other. E says when a trait follows an autosomal recessive inheritance, both males and females are affected with the same frequency, and the trait can skip generations. When a trait follows a Y-linked inheritance, affected fathers produce 100% affected sons. Affected sons, not affected. Sometimes not affected. All right, for F, sampling error is high when analyzing the inheritance of traits in humans because the sample size is typically low. And for letter G, the purpose of the chi-square test involving genetic problems, for the purposes of the chi-square test involving genetic problems, the degrees of freedom equals the number of phenotypic classes minus 1. DDD, that's all, folks.